Welcome back to my channel. Today, we're diving into a fundamental concept in electrical engineering: constant properties of transmission line. If you are visiting my YouTube channel for the first time, don't forget to support the channel by liking and subscribing to the channel. Hit the notification bell, so that you will be notified whenever I post important tutorial like this. Today, our concern is to study the inherent properties of transmission lines, and to know how does these properties behave when alternating current passes through transmission lines. Now, it is crucial to understand that when a conductor carries current, particularly alternating current, it generates both magnetic and electric fields around it. The interaction between the magnetic and electric fields in the conductor alters the expected performance of the transmission lines. This effect brought us to the topic of today: the properties of transmission lines. These characteristics become inherent whenever the AC lines are energized. These transmission line properties are typically considered fixed, or constant parameters, because they are generally assumed to remain unchanged along the length of the line, provided certain conditions are met. These conditions includes uniform construction, constant frequency of the AC supply, and linear characteristics throughout the lines. The behavior and efficiency of a transmission line are heavily influenced by these key properties. The transmission line has mainly four properties, which are resistance, inductance, capacitance, and shunt conductance. These parameters are uniformly distributed throughout the line. Hence, it is also called the distributed parameters of the transmission line. In their configurations, inductance and resistance give rise to series impedance, while capacitance and conductance contribute to shunt admittance. Now, stay tuned as we begin. Welcome back. What is effect of resistance on a transmission line? The resistance of a transmission line refers to the opposition that the line presents to the flow of electric current. It's caused by the conductors, typically made from materials like copper or aluminum. Resistance is essential because it affects how much power is lost as the current travels along the line. High resistance can lead to significant energy loss, which is why transmission lines are designed to minimize this property. For long-distance transmission, low-resistance materials and thicker conductors are commonly used to improve efficiency. Note that resistance of transmission lines increases as distance grows. To reduce this, use allowable-sized conductors and high-conductivity conductor. This property of transmission lines is the simplest. Now that we've explored how resistance impacts transmission lines, let's move on to another crucial property: the inductance of transmission lines. In the medium and long transmission lines, inductance is more effective than resistance in value. As I mentioned earlier, the transmission line possesses dual fields, magnetic field and electric field properties. Let's take a look at the impact of the magnetic field. When alternating current flow through a transmission line, varying magnetic flux is generated around the conductor surface. This varying magnetic flux line induce EMF in the line. This is accordance with Faraday's law. This induced EMF in the line is resulted as parameter known as inductance. For proper understanding of Faraday's law, you can watch my video on Faraday's law through the link in description box below. Let's proceed. Analyzing this inductance further, the magnetic flux linking with the conductor consists of two parts, namely, the internal flux and the external flux. The internal flux is induced due to the current flow in the conductor. This is called self-inductance. The external flux is produced around the conductor is due to its own current, and the current of the other conductors place around it. Note that external flux due to current of the other conductor's place around it is called mutual inductance. It's important to know that the total inductance of a transmission line is directly proportional to its length, meaning it increases as the line gets longer. Now that we've covered inductance, let's explore its impact on transmission lines. There are several key effects to consider. 1. Voltage drop. Inductive reactance causes a voltage drop along the transmission line, which can lead to a reduction in the received voltage. 2. Current limitation. Inductance limits the rate of change of current in the transmission line, which can affect the transmission of high-frequency signals. 3. Phase shift. Inductance causes a phase shift between the voltage and current waveforms, which can lead to distortion and interference. 4. Resonance. Inductance can cause resonance in the transmission line, leading to voltage and current amplification at specific frequencies. 5. Attenuation. Inductance contributes to the attenuation of high-frequency signals in transmission lines. 6. Distortion. Inductance can cause distortion in the transmitted signal, especially at high frequencies. 7. Oscillations. Inductance can cause oscillations in the transmission line, leading to instability and interference. Now, how can we reduce this occurrence? To mitigate these effects, transmission line engineers use various techniques, such as 1. Using shorter transmission lines or segmenting longer lines. 2. Increasing the conductor size or using multiple conductors. 3. Using inductive compensation or filtering. 4. Implementing impedance matching or termination techniques. 5. Selecting transmission line materials with lower inductance values. Now that we've explored how inductance affects transmission lines, let's move on to another crucial property, the capacitance of transmission lines. Capacitance in a transmission line arises from the electric field created between two conductors. The conductors of the transmission line act as a parallel plate of the capacitor, and the air is just like a dielectric medium between them. As the alternating current is passing through the conductor, electric field is established outside the conductors between the two lines. This electric field charges the surrounding air, which serves as dielectric medium. This occurrence creates property of line called capacitance. The charging and discharging of the surrounding air is simultaneous process, as the current is alternating current. This constitutes of power losses by charging of surrounding air. Now, note that the total capacitance of the line is proportional to the length of the transmission line. This makes the capacitance becomes negligible on short lines and low voltage transmission line. In the case of high voltage and long lines, it is considered as one of the most important parameter. You can check out my video also on AC transmission line model to understand properly what I mean by short, medium, and long line transmissions through the link in description box below. Now that we've covered capacitance, let's explore its impact on transmission lines. There are several key effects of capacitance on transmission lines to consider. 1. Signal attenuation. Capacitance causes signal attenuation, especially at high frequencies. 2. Phase shift. Capacitance introduces a phase shift between the voltage and current waveforms. 3. Resonance. Capacitance can cause resonance in the transmission line, leading to voltage and current amplification. 4. Signal reflection. Capacitance can cause signal reflection, especially when the transmission line is terminated with a mismatched load. 5. Power loss. Capacitance can lead to power loss in the transmission line, especially at high frequencies. 6. Crosstalk. Capacitance can cause crosstalk between adjacent transmission lines. 7. Signal delay. Capacitance can cause signal delay, especially in long transmission lines. 8. Oscillations. Capacitance can cause oscillations in the transmission line, leading to instability. Now that we've explored how capacitance affects transmission lines, let's move on to how to mitigate it. 1. Length of the transmission line. Use shorter transmission lines or segmenting longer lines. 2. Conductor size and shape. Increase the conductor size or using multiple conductors. 3. Using capacitive compensation or filtering. 4. Spacing of the conductors. 5. Selecting transmission line materials with lower capacitance values. 6. Frequency of the signal. Avoid using high-frequency transmission. Now that we've explored how capacitance affects transmission lines, let's move on to last crucial property, the shunt conductance of transmission lines. Note that whenever electrical current flows in a path that it doesn't supposed to, it becomes leakage current and losses. When the alternating voltage applies in a transmission line, some of the current flow in the dielectric medium because of dielectric imperfections. Shunt conductance represents this leakage of electric current from the transmission line to the surroundings. It is a measure of how much conductive material around the line is. High shunt conductance can lead to signal loss and reduced efficiency, as some of the power intended for transmission could be dissipated to surroundings. High shunt conductance means high current leakage. Therefore, keeping shunt conductance low is crucial to maintain signal strength and reduce losses. Now that we've explored how shunt conductance affects transmission lines, let's move on to how to mitigate the effect. 1. Insulation materials. Use high-quality insulation materials with low dielectric losses and high resistivity. 2. Insulation thickness. Increase the insulation thickness to reduce the electric field strength and minimize leakage currents. 3. Conductor spacing. Increase the spacing between conductors to reduce the electric field strength and minimize capacitance. 4. Shielding. Use shielding materials, such as copper or aluminum, to enclose the transmission line and reduce electromagnetic interference. 5. Cable design. Optimize cable design by using a larger conductor diameter. 6. Frequency reduction. Reduce the frequency of the transmitted signal, as shunt conductance increases with frequency. 7. Pressurized cables. Use pressurized cables, which can reduce moisture ingress and minimize shunt conductance. 8. Cable drying. Dry the cable to remove moisture, which can contribute to shunt conductance. As we explore the effect of lines' properties, please pay attention to these important insights and key points about the 4 transmission line properties we've discussed so far. 1. All the 4 properties increases as length of the transmission line increases. 2. Apart from resistance, the rest increases as frequency of the transmission line increases. 3. All the 4 properties reduces, as the size of the conductor increases. 4. Apart from resistance, the rest can mitigate through shielding techniques. 5. Inductance occurred due to alternating magnetic field, while capacitance effect is due to electric field outside the conductor. 6. Phase shifts are caused by inductance, capacitance, and shunt conductance, but resistance has no impact on phase shift. 7. Shunt conductance occurred due to dielectric strength breakdown, or insulation breakdown of the surroundings. 8. In DC transmission lines, the effects of inductance, capacitance, and shunt conductance are relatively insignificant compared to AC transmission lines. In conclusion, To wrap it up, understanding resistance, capacitance, inductance, and shunt conductance can help us grasp how transmission lines operate, and how we can optimize transmission lines design and performance. If you found this tutorial helpful, don't forget to like, share, subscribe, and leave your comments or questions below. Thanks for watching.